This video is on solving basic quadratic equations using the square root property. This is also sometimes called the principle of square roots or extracting roots. So here we have the square root property. If you have something squared equals a constant, in this case the k is the constant, then x is equal to plus or minus the square root of the constant. So that's the square root property. And the x is capitalized because x may not be just a variable, it could be an expression as well. And in algebra, we typically do that. We use a capital variable to represent expressions. So we will be able to use this for a lot of different scenarios. And actually, in application, the square root property works great in physics. A lot of physics equations and mechanics equations are basic equations that have quadratic relationships, like in time or velocity or something like that. And so this approach to solving equations becomes useful in physics. So let's take a look at a couple of basic examples of the square root property. They're real short ones. So here we have two basic quadratic equations. The first one is the variable r. R squared plus 6 is equal to 30. So we're going to find the value of r. Now the exponent of 2 is indicating that we're going to probably have two roots to this equation. So when we solve this equation, we should expect two roots, or at least two roots. Sometimes you get a certain case where you only get one root, and we'll see that case in a different video. Mostly that comes up with quadratic formula. So here we go. R squared plus 6 is equal to 30. Let's solve for r. Now I always tell my students to rewrite the equation as you transfer it from the problem out of the book or out of a worksheet, whatever. So we're going to go ahead and write this. If r squared plus 6 equals 30. Now if we're going to use the square root property, we need to get the equation set up so that we have the variable squared equals a constant. So that means we got to isolate r squared. So we have to do a little bit of algebra first. We're going to move that 6. I'm going to use inverses to make that happen. So the inverse of 6 is a negative 6. So I'm going to add a negative 6 to both sides of the equation. Now since I am using the additive inverse, I'm going to go ahead and put a sum line in there. And I'm going to use the lazy canceling notation. So these cancel out, so we can cross them out. So we're left with r squared equals 24. And now it's set up perfectly to use the square root property. We have something squared, or r squared, equals a constant. So we're ready to go ahead and extract roots. So from the square root property, we get then that r has to be equal to plus or minus the square root of 24. That's the consequence of the square root property. And now we see how we get our two roots out of this. There's going to be a positive root and a negative root. Now if we look at the 24, 24 is not a perfect square, so we're not going to get nice integer values out of this. We're actually going to get irrational roots. So we have to simplify this if we can. Now one option is also to approximate with a calculator, but I'm going to go ahead and simplify this in terms of radicals. So we're going to go ahead and rewrite this as r equals plus or minus, and then I'm going to factor underneath the square root symbol. And the perfect square that actually divides 24, which is why this is actually possible, why simplifying is possible, is 4. Now, if you don't have your perfect squares memorized, you should go ahead and have them at your side when you're doing any topics like the quadratic formula or the square root property or Pythagorean theorem. You want to just know those squares. That would be the best thing to do, is just to know the perfect squares, at least up to 20 squared, which is 400, or at least have them in a list at your side. Okay, so this will factor as 4 times 6. 4 times 6 is 24. And there we can take the square root of 4 because 4 is on the list of perfect squares. So therefore r equals plus or minus 2 radical 6. So the two roots are a negative 2 root 6 and a positive 2 root 6. And I get a little lazy how we say that. 2 root 6 actually means 2 times the square root of 6. The 2 written right next to the radical symbol is implying multiplication. After all, we did factor it here, so we can remember that. This is 2 times the square root of 6. And that's one way to calculate this in a calculator. Actually, you can type in the square root of 6, get your calculator to approximate it, and then multiply by 2 to get the actual approximate root. We can also write these as a list as well. And we'll do that on some of the other examples. So let's go ahead and solve the other equation. The other one's also very short. We have 2x squared equals 72. So we just have this coefficient out in front of the square. With the square root property, we do need to make sure that we have the variable isolated completely. So we got to multiply by 1/2 to cancel out that 2. Or alternatively, we can use division notation. And by the way, multiplication by 1/2, which is the inverse of 2, is equivalent to division by 2. And I know students like to do the division on the fly, so we can divide that out. So that's one way to handle that. And of course, the 2's then divide out, and we can even show that. And that's going to give us x squared equals 36. All right, so now x squared equals 36. We have the equation set up perfectly to extract roots. So we have something squared equals a constant, so we're ready to go ahead and write this as x equals plus or minus the square root of that constant. Now, in this case, 36, we got a perfect square there, so this will be easy to calculate. We're going to get 2 rational roots plus or minus 6. So these are considered, basic quadratic equations that we can solve using the square root property. Let's look at something a little bit more interesting or a little bit more complicated. So here, this one, sort of a little bit of a word problem, not too bad. It says solve for x in the quadratic equation below. Give the roots in radical form. So that's telling us that we want to have the radical symbol or the square root symbol left in our final answer. And we're hoping that this will be easy to solve using the square root property. If it's not, we would have to use a technique that's a bit more powerful, like the quadratic formula, or potentially the completing the square algorithm, which technically the completing the square algorithm and the quadratic formula are the same thing, and we'll see that in a future video. But let's go ahead and solve for x on this one. So we got to get it set up so we can extract roots. That means isolate the squared part of the equation. So I'm going to add 1 to both sides. That'll be a step in the right direction in isolating the squared part. All right, I'm using the additive inverse. I'm going to put a sum line in there. So these cancel out, so we're left with 6x squared. Probably should show that they canceled, equals 72. Now we can multiply by 1/6 on both sides to cancel out the 6 in front of the x squared. But division is convenient on the fly, so we're going to go ahead and divide out the 6. Remember, multiplication by 1/6 and division by 6 are mathematically equivalent. So it's certainly permissible to do that. So those cancel out, and we're left with x squared equals 12. And then we're ready to extract roots. We have something squared equals a constant. That's where we can go ahead and write this as x equals plus or minus the square root of that constant, which is 12. Now 12 is divisible by a perfect square. Now, if for some reason the number underneath the square root, which we call the radicand, is not a perfect square, then we would simplify it as much as we can if it's divisible by a perfect square, or if it's not a square, we have to leave it as is. But radical 12 definitely simplifies, so we can write this as a product. And just like the previous example that we solved earlier, we can factor out a 4. So it's 4 times 3. So the 2 roots, completely simplified, is plus or minus 2 radical 3. Now on this one, I'm going to go ahead and write out the solution set as a list. So x is equal to, and then we'll use the braces. Now let's use what we call set roster notation. So we put the roots in order, so the negative 2 root 3 would go first, and then the positive version of that goes second. And there's our solution set. Now it's also certainly possible to approximate these using a calculator. We can just type in, actually you can go back and just type in the square root of 12 in your calculator to get the approximation of the roots. Or you can type in the square root of 3 in your calculator and then just multiply by 2. So either way we can definitely get approximations to the roots. And the upside of the approximations is that they're easy to type into a calculator. Type into a Canvas or whatever. Okay, so let's go ahead and solve another example. We're kind of stepping up in difficulty level as we go. So this one is going to give us roots that are going to be in binomial form. And I think we're going to have to use a specialized technique for calculating square roots on this one. Okay, so if we're going to use the square root property, we definitely need to get to this situation where we have something squared equals a number, or something squared equals a constant. So we have a bit of work to do to make that happen in this equation. I think we'll go ahead and move the 4 first. Better write the problem here again. So we got 4 minus, that's supposed to be a 4. So it looks like a 4. There we go. So 4 minus the quantity u minus 3 squared equals 53. Make that look more like a 4. Okay, so now we got to move that 4 using the additive inverse. So the inverse of positive 4 is negative 4. So we'll subtract out 4 on both sides of the equation. And again, when I use the additive inverse, I like to put a sum line in there. So these cancel out. Notice the negative sign is still there. So the negative sign is attached to the quantity u minus 3 squared. And 53 minus 4 is going to give us 49. Now we can go ahead and either divide or multiply by a -1 to completely isolate the squared part of the equation. You can do this without showing too much if you want. You can just multiply both sides by -1 in your head. Just be really careful if you do it that way. I'm going to go ahead and just use division notation just to make it abundantly clear what we're doing. So we're going to divide both sides by -1. And of course that means the negativity goes away on the left hand side of the equation. So we just get the u minus 3 quantity squared equals a -49. Now we're ready to extract roots. The reason that is because we have something squared equals a constant. This is why in the square root property we typically use a capital X in here. I know the variable is not X, but the variable doesn't really matter. It can be any variable we want. But it's capitalized because it is potentially possible to have an expression squared equals a constant. And so we're covered by the square root property. So we can go ahead and extract roots now. So the u minus 3 then, just the u minus 3 without the square, is equal to plus or minus the square root of a -49. Now 49 itself is a perfect square, but we have this issue of a negative number underneath the square root symbol. That adds an extra element to the problem, something interesting. Let's go ahead and recall what we're going to use here. When we went over square roots, we had this interesting assumption made by the famous mathematician Leonhard Euler. He wanted to solve equations like this, and for a long time mathematicians were sort of stumped on how to deal with the negative sign underneath the radical. And so Euler made this assumption. He had a symbol he called I squared. I squared is equivalent to a -1. So if something squared equals a -1, that was the challenge. What can you square and get a -1? And it's not really obvious what that is. But if you follow with his assumption, that we get that I then must be the square root of a -1. And so we have this number I. In algebra, a scripted I is a number. Kind of like the lowercase pi in geometry is a number. So I is equivalent to the square root of a -1. So we're going to use Euler's assumption to help us find the roots to this equation. So I'm going to go ahead and simplify the radical. And I think I'll just do that on the side over here. We're going to take the square root of a -49. So I'm going to factor this as the square root of 49 times the square root of a -1. And the square root of 49 is 7 because 49 is a perfect square. So we get 7i. So down here in our equation, we can write u minus 3 equals plus or minus 7i. And then to finish solving for the variable, we just need to use the additive inverse and add 3 to both sides of the equation. And this is what I meant when I said the roots are going to be of binomial type. So these are going to cancel out, and we get u equals 3 plus or minus 7i. So just like last time, we can go ahead and list this as a solution set. So we're going to say u equals 3 minus 7i, or u can equal 3 plus 7i. And there's the two roots that are in binomial form. So interesting number I, and it turns out that number I has a lot of valid applications within mathematics and physics. So it's not artificial. Don't think of we call it the imaginary number I. The word imaginary is not so much that it's make-believe, but it's a reference to Euler's thinking when he first developed this. This is Euler's imagined root, and when he made this assumption and took it and ran with it, he essentially developed an entire branch of mathematics called complex analysis. So the number I in algebra is definitely a big deal. All right, let's see if we can fit in one more example. We'll do this one a little bit faster. So this one is actually a special type of equation. Normally we wouldn't be able to use the square root property directly on this. We'd have to use the completing the square algorithm. This one's actually set up in a very convenient way because 25 is actually a perfect square. So my curiosity would say, hey, maybe this thing is a square. The 16x squared plus 8x plus 1. Well, if you look at the coefficient 16 and 1, constant out here, they're both perfect squares. So if the middle term is 2 times the things that we squared to get those numbers, then we actually have what's called a perfect square trinomial. So what I'm referring to is these formulas from polynomials. These are the formulas for squaring a binomial. So this is what perfect square trinomials look like. They are squares of binomials. So I'm thinking that this thing is a perfect square, and in fact, indeed is. Because if you take the square root of 16 is 4, square root of 1 is 1. So if you take 4 times 1 and double it, you get 8, and that's the middle term. So it's fitting this formula exactly. So I'm going to take advantage of that and write this as a square of a binomial. So if you're good at factoring, you would see this right away. But actually, when you factor this thing, it's going to be 4x plus 1 quantity squared equals 25. And you can check that by actually squaring the polynomial 4x plus 1. You can even check it by just using this formula. You take the leading term a, square it. So 4x times 4x is 16x squared. That gives us our first term. The last term is b squared is 1. And then the middle term is 2 times the product of these. 1 times 4x times 2 is 8x. So definitely we know that's factored correctly. And now we're ready to extract roots because we have something squared equals a constant. So the 4x plus 1 equals plus or minus the square root of 25. And it looks like we're going to get nice rational roots here because the 25 is a perfect square. So therefore, 4x plus 1 equals plus or minus 5. At this point, we have no choice but to keep that plus or minus in our work until we isolate the two different roots. So we're going to go ahead and solve for x by subtracting 1 on both sides. Again, put a sum line in because we use the additive inverse. These cancel out, so we get 4x is equal to a negative 1 plus or minus 5. And then last step is to divide out the 4 or multiply by 1/4 on both sides of the equation. And we have our two roots. So x is equal to a negative 1 plus or minus 5 over 4. Now we have to go ahead and apply the plus or minus now. So x is equal to a negative 1 minus 5 over 4. And this would be a negative 6 over 4, which reduces to a negative 3/2. So that's one of our roots, one of our rational roots. The other root is x is equal to a -1 plus 5 over 4. And that's going to give us 4 over 4, or 1. So there's our two roots to our equation. And just like before, we can go ahead and write it as a list. So x is equal to -3/2 and 1. We write those in order in the set roster notation. So sometimes certain equations can be manipulated a little bit to make the square root property work. And in fact, that's the guiding principle behind the completing the square algorithm, which is something we'll cover in a different video. So anyway, these are basic quadratic equations using the square root property. Of course, this is a limited technique. Sometimes equations don't fit into this property that we're working with. So if it doesn't work, then we either need to manipulate it quite a bit using this completing the square algorithm, or break out the quadratic formula. So you'll see that in a future video. Thanks for watching. Hopefully you got a lot out of this. And I will tell you, if you're going to be a physics student, you will use this property in physics class.